Hello and welcome back to Educator.com and welcome back to Biochemistry. So in the last several lessons we discussed glycolysis, and we finished discussing glycolysis. So today we're going to start talking about gluconeogenesis, which is, instead of the breakdown of glucose, this is how the body actually makes glucose when it needs to do so. Now, you're going to see in a minute that a lot of the reactions of gluconeogenesis are the same. They're just run in reverse. However, it isn't just glycolysis run in reverse. If you remember, in the glycolysis reactions, there were three reactions in particular that were highly exergonic, very, very high negative free energy. So they're virtually irreversible under physiological conditions. Well, because they're irreversible, there's no way for the enzymes to actually go backward, just reverse glycolysis. So those particular reactions, gluconeogenesis actually bypasses and uses its own set of enzymes for its metabolic pathway. So let's go ahead and write all this down formally and see what's going on. Okay, so let's see. We'll stick with black today. So oftentimes the body needs to synthesize glucose instead of breaking it down. Needs to synthesize glucose instead of breaking it down. Okay, so we will concentrate on the gluconeogenesis that takes place in the mammalian liver. So we will concentrate on how the mammalian liver does this. Okay, so gluconeo, I'll just call it that for short. Gluconeogenesis is not the reverse of glycolysis. Not just the reverse of glycolysis. Okay, so now we can start. Recall, there are three glycolytic reactions. Glycolytic reactions that are irreversible under physio conditions. Okay, so let's go ahead and list what they are. The first one, we have glucose going to glucose 6-phosphate. We had a delta G, and in parentheses, I'll just write physio delta G. And notice there's no standard, no degree sign, so these are actually under physiological conditions, not biochemical standard conditions. So negative, somewhere in the range of negative 33 kilojoules per mole. And then the second reaction is going to be the fructose 6-phosphate to the fructose 1,6-biphosphate. That one carries a delta G of about negative 22 kilojoules per mole. And the last is the phosphoenol pyruvate to pyruvate. That's the final reaction in the glycolytic sequence. And this one carries a delta G of, under physio conditions, of about minus 16, minus 17 kilojoules per mole. So all of them irreversible, so gluconeogenesis has to bypass these reactions. It can't just use these reactions. So, excuse me, so gluconeogenesis bypasses these steps with its own set of enzymes. With its own set of enzymes. And these reactions are themselves sufficiently exergonic to make sure that gluconeogenesis is irreversible. Are sufficiently exergonic to make sure that gluconeo is irreversible. Well, are sufficiently exergonic to make sure that gluconeogenesis is, well, let me go ahead and, to make sure that they are irreversible in themselves. They are irreversible. So it's the reactions that are irreversible. Essentially, it's going to commit to gluconeogenesis. So it's not going to back down, somewhere in the middle. These particular reactions themselves are highly exergonic to push gluconeogenesis forward. Sure that they are irreversible themselves. Let's just go ahead and say it that way. Okay, so let's go ahead and take we're going to look back at a schematic. I'm going to draw it out of glycolysis, and I'll show you where the bypass reactions take place. So let's go ahead and do this one in